Okay, so hopefully you've got the idea of how to do a definite integration now. Now I'll warn you, this next bit is quite difficult, so make sure you're happy with the first part of the video before you move on to this bit. Go back over the examples, have a look at some questions maybe, make sure you can do definite integration because this next bit is quite tricky. Now the area under a curve is given by integrating the equation of the curve, okay? This is kind of like a geometric interpretation of what integration actually is. So when we differentiate, you'll probably remember that we get the gradient of a curve when we differentiate. So actually when we integrate, we get the area underneath the curve. That's actually what integration does. To give you an example, here's a curve. This is y equals x squared. Say I wanted to find this green area here. Now it goes all the way from 0 up to x equals 5. Okay, say we wanted to find all this green area. This is how we'd find it. We do the integration of the equation of the curve, which is x squared, and we put in the limits of where we want the area. We want the area between x is 0 up to x is 5. So that's where we get our lower limit of 0. This is our lower limit. And this is our upper limit. Okay, so if you work out that expression, and we'll do some examples of this, that will be equal to the area underneath that curve. Here's another example. This one's a parabola. It's an x squared graph, a negative x squared graph. If I wanted this green area again, you can see it's between 1 and 3. Okay, and it's always the area down to the x-axis that you find when you do an integration. So it's the area to the x-axis. So if we wanted this green area, we'd integrate that curve, but with our limits as 1 and 3 this time. So hopefully you can see how we can set up these questions. If we want the area, all we do is integrate the equation of the curve and put in the limits of where we actually want the area. Okay, and a graph's really useful here to see where the limits are, and you'll often be given a graph in the question. So let's have a look at some examples of this in action. Okay, so let's say we've got a curve C and I've given you the equation of the curve. And this is kind of just some exam question speak here, but you need to get used to it. So I've given the curve the name C, and I've said the region R is bounded by C, or bounded by C, and the lines x equals 0 and x equals 1. Now that sounds like nonsense. What we mean is it looks like this. Here's the equation, y equals 4x cubed minus 6x plus 10 graphed, okay? This red line here. Now it says it's bounded by C, and the lines x equals 0, which is this line here, and x equals 1, which is this line here. Okay, so that is the region R, which I've written the big R in and shaded it in green. They'll sometimes give you a sketch, sometimes you might have to do one yourself, okay? But hopefully you can see how I've translated that question into a graph. Just draw the graph. I appreciate this one's not a very easy one to draw. They would give you it if it was a difficult one to draw like this. And look at where it's bounded by. And the area goes down to the x-axis as well. So we want to find the area of R. The first step is to see how do we actually write a definite integration for this area. Well, what we do is we said we're going to integrate this curve between the two limits. Now, at this time, we're between 0 and 1, aren't we? There are limits of where we want the area. So we're going to integrate our equation between 0 and 1. So what I'm going to do is substitute in our equation. Okay, so you can see what I've done there. I've substituted in our equation for the curve, and we've said we want the area between 0 and 1, so they become our lower limit and our upper limit respectively. All I'm going to do now is actually integrate that curve. So if I do the integration, 4x cubed integrates to x to the 4. Hopefully you should be familiar with this from the previous lesson. Minus 6x becomes minus 3x squared. And when we integrate a constant, all we do is put an x on the end, so we get plus 10x. And here again, I'll put the limits. This is the upper limit, this is the lower limit. Okay, the square brackets mean I've done the integration, but I haven't done the limits yet. And that's what we're going to do here. So this looks pretty complicated, but it's not too bad. All I've done is taken this expression and substituted in the upper limit for this part. Okay, the upper limit's 1, so instead of x to the 4, I get 1 to the 4. Instead of minus 3x squared, I get minus 3 times 1 squared. And instead of plus 10x, I get plus 10 times 1. So I've just substituted the 1 in everywhere I see an x. That's my upper limit. And then I subtract, because we do the upper minus the lower. And this is my lower limit subbed in, which is really easy because the whole thing is going to be 0. Instead of x to the 4, I get 0 to the 4. Instead of minus 3x squared, I get minus 3, 0 squared. Instead of plus 10x, I get plus 10 times 0 because I've substituted in 0 every time I see an x. If I simplify all that down, 1 to the 4 is 1, minus 3 plus 10, which you'll find gives you 8, and this whole bit has got zeros in, so you get 8 minus 0. You can just stick all this in the calculator if you want, and there's your answer. So actually the area underneath that curve is 8 units, okay? That's how big that region R is, okay? And that's how we find the area underneath the curve. And I've got a few more examples for you to have a look at on this. So let's have a look at another example. This time we've got a more complicated expression, quite a lot more complicated. We've got square roots and 5 over x squared here. It's quite a tough one. But it's the same principle here. We've got a region R bounded by the curve C and the lines x equals 4 and x equals 9. That looks something like this. Okay, so we've got the graph here of that function. This is y equals root x minus 5 over x squared plus 3 between 4 and 9. Okay, now we're going to use those as our limits for the integration. So we're going to integrate between 4 and 9. And that's what we see here. All I need to do is substitute in the expression for my curve, which is all of that. Now hopefully you can see here, what I've done is I've converted the square root of x to x to the half, and 5 over x squared to 5x to the minus 2. Hopefully you remember that from the indices and surds lesson and also the earlier integration lessons. It's just changing it to normal, to regular powers, makes it a lot easier to do this integration, so please do that before you try and integrate. The next step is to actually do the integration. It's a pretty tough one. I'm not going to go over it in any great detail because the indefinite integration lessons will show you how to do this. I've increased the power by 1 here and then divided by it. Same here, increase the power by 1, ended up divided by -1, which gives me a plus sign instead of a negative. And when we integrate a constant, we just put the x on the end of it. Okay, so it's a pretty tough integration. But my upper limit and my lower limit are still here on the outside of the bracket to say I've done the integration, but I haven't done the limits yet. That's what we're going to do in this stage. This looks really nasty, but if you just follow it through, it's not too bad. Here's my upper limit here that I've substituted in. So 9 was our upper limit. So everywhere I see an x in the expression, I've substituted in 9. So instead of 2/3 of x to the 3 over 2, I've got 2/3 of 9 to the 3 over 2. Instead of 5x to the minus 1, I've got 5 times 9 to the minus 1, and so on and so on. Okay, and that gives us the expression for our upper limit. And this is our lower limit over here. I've substituted in 4 everywhere I see x instead. So instead of x to the 3 over 2, I get 4 to the 3 over 2, and so on and so on. Okay. Because there's a lot of terms in this one, it's probably better to either work out each term one at a time, or work out this part here, the upper limit, then work out the lower limit, then subtract them. If you put everything in your calculator, there's a good chance you'll end up with a wrong sign or something like that. It's easier to do this one in parts, I would say. If you have a look, each term you find here, this is just from putting in the calculator, which gives us an overall answer, not very nice one, of 971 over 36. Okay, so that gives us an area of this region R. Okay. I'm afraid the examples get even harder. So this is kind of an interesting example. We've got the equation y is x squared minus root x, and we want the between x equals 0 and x equals 1.5. Okay, the problem with this one is part of the area is underneath the x-axis here, and part of the area is above the x-axis here. Now, you might think, well, I need to integrate between x is 0 and x is 1.5, so I'll do this. I'll integrate it between 0 and 1.5. That would be a mistake. That won't give you the correct answer. And the reason why is quite complicated, but you'll see in this example. Basically, this area will come out in the integration as negative because it's below the x-axis. Now, we don't want that area to be negative because to us it's a positive area, right? It takes up some area, so it being negative makes no sense. But unfortunately, when you integrate, it will come out as negative. This bit's fine. This will come out as positive. Okay? The way we get around this is we integrate each bit separately. So this bit will integrate, and then we'll integrate this bit. So we'll do it in 2 sections. That way we can see what the answer is from this first part. It will be a negative number, but we can just flip it and make it positive because we don't want a negative. We'll work out the area from here as well, So this is like area, well, we'll call it R1 and R2. So R1 is going to be negative, but we'll flip it round, and R2 is fine, and we'll just add the two together to get the total area of R. So to start with, I'm going to look at this first area, R1. Okay, so this is for R1. I substitute in my expression for the curve. Again, instead of square root of x, I've written x to the half. Yeah, so instead of root x, I've written x to the half. Okay, so all I'm going to do now is integrate this. That gives me x cubed over 3 minus 2/3 of x to the 3 over 2. It's a tough integration, this one. Have a look in the previous lesson if you're not sure about it. And again, I'm just integrating up to 1, because I said I'm going to do these two sections, R1 and R2, separately, so I'm only integrating up to 1. I substitute in the upper limit, so I've substituted in 1 here. So the upper limit is here and here. So everywhere I see an x, I've substituted a 1 instead. And then subtracted off the lower limit, which is 0, so substitute zeros in. And you'll find that gives you 1/3 from here, 2/3 from here, and then this whole bit here is 0, because it's just 0 substituted in. So you'll find that gives us minus 1/3. And as I said, the area of R1 is indeed negative, and it's because it's below the x-axis. Okay, so when you have a curve you need to integrate, and it's below the x-axis, or part of it's below and part of it's above, like we have now, integrate the two bits separately. Do the bit below first, and then do the bit above, and then we'll figure out how to combine them later on. Because I've got negative 1/3 here, which what I'm really going to say is actually that has an area of 1/3. Okay, even though the integration tells us it's negative 1/3, we don't want a negative sign because a negative area makes no sense to us. So we'll just say actually that's actually 1/3. Okay. We're now going to deal with this area here. So this is for R2. Okay, between 1 and 1.5. So again, I've substituted in the equation of the curve. Again, I've used x to the half instead of root x. I integrate it, which obviously gives me exactly the same as what I had before. Okay, because I'm integrating the same equation. Here's where it gets different because I'm substituting in different limits. So the upper limit is here. This is all the upper limit. So I substitute in 1.5. And I substitute in 1.5 here. So everywhere I see an x, remember, I just substitute in the upper limit. Then I do a subtract. And then I substitute in the lower limit, which is 1 in this case. Okay. So here we said we were doing lower limit of 1, upper limit of 1.5. Substitute them both in. And basically you can just stick all that in your calculator and you'll find that gives you an area of 0.2336. It doesn't come out as a fraction, this one. So we're going back into decimal here. Okay, so this area is 0.2336. This area we said would be negative, but actually the area of it is 1/3, okay? Because a negative area makes no sense to us. So to find the total area, all I do, add them together. And I find that the total area is 0.5669. Now, if I try to do the integration all at once by going all the way from 0 to 1.5, it wouldn't have given me 0.5669 because it would have taken this negative 1/3 and it would have given us 0.2336 minus 1/3, okay, which would have given us the wrong answer, okay? So if you have an area that's underneath the x-axis, make sure you integrate them both separately, okay? If you're just asked to do, so if the question has got nothing to do with finding the area, it just says do this integration, okay? I don't know, let's say it's something like this. You wouldn't do those two bits separately, you just stick the upper limit and the lower limit in as normal. It's only when we're finding the area that you do the two parts separately. If it's just a straight up definite integration, nothing to do with area, just do exactly what it says, put the limits in, don't split it up, okay? But if you've got an area, split up into the bit below the axis and the bit above the axis. And I'm afraid it gets even harder still. We get something here called compound areas. We have an integration that we have to do, but it doesn't give us the result directly. So you'll see an example here. So I've got a curve C and the line y equals 4. Have a look at the graph to see what I mean. So this is the line y equals 4. And this is the curve y is x squared minus 7x plus 14. Right, this is the area we want here. Now, how do we work that out? First thing to notice is this curve crosses at 2 and 5, which it tells us in the question here. That information is given to us, although we could actually work that out by solving the quadratic. So how do we get that region R? Now, if we integrate that curve between 2 and 5, what would we get? Well, actually, the area underneath the curve is all this here, isn't it? It's all this bit. It's not the area we want, but it helps us. Can you see there's a rectangle here? A, B, C, D. It's kind of marked out by these two dotted lines, that black line and the x-axis. Now, that area R is given by the area of the rectangle, which I'm outlining here, minus that red shaded area, which is the area under the curve. Can you see how that gives us R? We take the rectangle and we take off the area under the curve. Now, I've just marked on the dimensions of the rectangle out, which we're going to use in a second. But what I've said here is that R is the area of that rectangle minus the area under the curve. Okay, so I'm having to use a bit of logic, a bit of kind of making up a rectangle here to actually get to the area of R. Okay, because you can see R's above the curve here, not below the curve. When we integrate a curve, we get the area below the curve. Okay. Now the area of the rectangle is pretty easy. You can see if you look on the y-axis, it's 4. It's got a height of 4. And if you look on the x-axis, it's got a width of 3. Okay, so the area of the rectangle is 12 units. That's dead easy. Okay. What about the area underneath the curve? Well, to do that, you can see I'm integrating between 5 and 2. Yeah, that's where I want the area under the curve, between 2 and 5. Yeah, so they're my limits, and I've put in the equation of the curve, and that's what I'm going to integrate. Okay. So that gives me this red shaded area here, which is the area underneath the curve. So let's figure out this area. So we're going to integrate everything first. So x squared becomes x cubed over 3. Minus 7x becomes minus 7 over 2x squared. When we integrate a constant, we just put x on the end. We're then going to substitute in the upper limit. Okay, so the upper limit is 5. Here it is. And the lower limit down here is 2. So everywhere I see an x, I substitute in a 5. So x cubed becomes 5 cubed. X squared becomes 5 squared here, and so on. That gives me all of this for the upper limit, and then I subtract, because I always do the upper limit minus the lower limit. Substitute the 2 in for the lower limit, all the way across here. Stick all that in a calculator, or more sensibly probably stick each term in, just to make sure you don't make any mistakes in the calculator. And you'll find that gives you 15 over 2. Okay, it's a tricky calculation to do, but if you take your time, you should be able to get the same answer as me from that. Okay, that's the area underneath the curve. Now we said right at the start, to get this area R, we do the area of the rectangle minus the area of the curve. Okay, so to get R, I do the area of the rectangle, which is 12, minus the area under the curve, which gives me a grand total of 9 over 2, or an area of 4.5. Okay. So we can sometimes do that where to find difficult areas, we look at how we can use other shapes to find the integration. That's quite a common example where we have a rectangle and the area under curve and we have to combine them together.